6 years, wanted to run through corrections for the questions I had posted for you on Wednesday, and then want to run through a couple of bits on Half-Life before you try some of those problems yourselves. So I had corrected question 9 on the Hangouts, so I've skipped that one, so I'm doing 4, 5, 6, 10 as you can see on the corrections here. And then I've got a little bit of work on Half-Life, and I just want to do a quick demo on a graph then after that. So that's the plan of action for this video. I wanted to run through these nice and quickly. I'm sure 4, 5, 6 didn't cause you too much hassle, but just to make sure we're clear anyway. So question 4 talked about how much energy is contained within a mass of 5 kilos according to the equation. So we've got Einstein's famous equation there, E equals mc squared, energy, mass, speed of light, nice and straightforward. So we know that C is going to be a constant all of the time. We know mass is going to be either given to us or we have to work it out, and the same energy we either is given to us or we have to work it out. So in these cases we have to get energy, in this case we have to figure out mass, and you can see 4 and 5 nice and straightforward. We just fill in what we've got: kilos, meters per second, and joules for energy then to finish off. And in question 5, exact same thing is being done. We've got mass in kilos, we've got speed of light, meters per second, and we've got our unit then to finish off. Energy is in joules. So quick multiplication on your calculator will get those two values for you without any hassle. In question 6, we had to work out the mass that was converted. So we're actually looking for M in this case instead of E, as we did in question 4 and 5. So exactly the same, pop in what you know, and then a little bit of algebra to move stuff around. So you can see what I've done there. I've got my c squared value is multiplying by the mass. So if I bring the c squared over to the other side of the equals, it becomes a divide. So it goes underneath the line. It goes underneath the 9 by 10 to the minus 14 joules. That's the value we have already. I've just put in the numerical value there, divide those in, and you end up with a mass. Don't forget your unit, kilos. Okay, nice and straightforward. So 4, 5, 6 I don't think caused anyone any hassle, but I just wanted to run through them quickly. Question 10, kind of similar to what was being done in question 9, but we just needed to look at a couple of different things. So the first part, you can see it's talking about Rutherford's experiment, where we have alpha particles being bombarding a nitrogen atom, and what we have, those two, our nitrogen atom and our alpha particle, are combining or colliding, whatever way you want to say it, and that is the result. So as you can see, I put down there, that's the same as a proton. It's a hydrogen atom with 1 proton, 1 electron. So it's essentially the same as a proton mass, boys. So the question asked for the mass before and after the reaction, and you can see I've split it up into the two parts there. You've got the nitrogen has a mass number of 14, so that's why I've got 14 multiplied by the U value, which is our atomic mass units, and how to combine that or convert it, I should say, into kilos. So we do 14 times that gives us this value here. For helium, we've got 4 times the same number, and it gives us that. Now, just to keep in mind, if we don't recognize there, you've got those two numbers and we're adding those together. But the thing I want to be clear on, you can see 6.642 by 10 to the minus 27. That's a smaller number than that one, because that's by 10 to the minus 26. You should recognize that nitrogen should be, or should have, a higher mass than helium. Therefore, the nitrogen number should be bigger than the helium number, which it is in this case. So just to be careful, and especially when it's to do with scientific notation, people easily get tripped up on that. So we've got those two values in kilos. All we got to do is add them together, and that's the mass before the reaction, as we've said. Then the mass after the reaction, do exactly the same thing. You got your oxygen, you got your hydrogen or your proton, and you multiply them out, add them together. And you can see then in this case we end up with essentially the same values, 2.9892 for before and 2.9889 for after. Now again, I've done a little bit of rounding and so on, so you can see that might be the issue there. The other thing is, I suppose, in the back of the book, it counted this number. It gave you this as the final answer, and I was having a kind of think and a look around it. Now the idea, I suppose, is if this proton is being emitted, you might have those protons coming together to form more alpha particles. So if you had loads and loads of these being emitted, that they might band up together and join up and then form a new a new helium atom or a new alpha particle, and then repeat the process again. So I was thinking that might be the case as to why. But for me, I think the idea would be that you still got to keep those together. And the thing, especially for our chemists that you guys know, we go back to our chemical equation, and you've got before and after, or you've got reactants and products. And conservation of mass says that the mass before a reaction should be equal to the mass after a reaction. And as I've mentioned, you've got two values there that are very, very close to one another, essentially equal. And that is, again, the only reason that they're not exactly the same is because of a bit of rounding I've done, as far as I could tell. So it checks out. It makes sense that the mass before a reaction and the mass after a reaction should be the same. And if it isn't, it is because of energy being released. And in this case, as we said, if energy were released in this reaction, so for the part B of question 10, I didn't make a note on it, but I want to discuss it now. For part B of question 10, it asks about energy being released in the reaction. Where would it come from? So we can see from the calculations that we've done that the mass before the reaction and the mass after the reaction is essentially the same. So there's no change in mass, really. There's no change in mass. Therefore, E is equal to mc squared isn't going to work for us. There's no change in mass, so I can't do E equals mc squared and figure out, oh yeah, we've dropped mass by a certain amount. If I multiply that by the speed of light squared, it will give me how much energy is given off. If there is no change in that m value, imagine if I write it down again, E is equal to mc squared. If I've got the same m value over this side before the reaction and the same m value after the reaction, my E value is going to be the same because this is a constant. Our c squared value is a constant always. So the only energy that could be released, or the only way that energy is being given off in this case, is by these particles and the movement of those. So there's nothing being given away in terms of mass, but this could be kinetic energy. And I would think, based on what I've discussed and how I've explained it to you there, we could have kinetic energy of this proton or this hydrogen atom moving at a very, very high pace. And you can imagine we could work that out by doing a half mv squared if we knew how much energy that was. A half mv squared, because we know our mass. We could either work out the velocity if it was given to us, or if we had the amount of energy that it was, we could work out how fast that was moving. Now, we haven't been given those values and we're not expected to do it, but just to give us an idea, I would think that that's where the energy would be coming from. So, to tie that in then, that's all of our corrections done. I wanted to finish off by looking at the next step, which is our half-life. Couple of notes I've written down there very quickly. It's essentially summarising what's in your textbook already. You can see we've got activity is proportional to the number of nuclei in a sample. So the higher the value, if one is going up, the other one's going up. If the one is going down, the other one is going down. Nice and simple. And again, whenever we have proportionality, there's always being multiplied by a constant. There always has to be a constant involved, and it's this lambda value. Again, we use lambda for wavelength. If you guys remember from stuff we've done on light and stuff we've done on sound previously, we also use it here as the decay constant. Okay, now as I said, it's a constant and it's a specific value that will be given to you, or that you can calculate based on everything that's happening. And as I said here, you can see it's different for each element or isotope. So if you're given radioactive carbon, or if you're given plutonium or uranium or whatever it might be, they'll all have different numbers. Two ways we can measure this activity, as we've said here. We can use the becquerel, named after Henry Becquerel, which is the unit for it. As you can see, it's 1 nucleus decaying per second. So we have one nucleus decaying per second. It is decaying with an activity of 1 becquerel. If we've got 5 nuclei decaying per second, it's an activity of 5 becquerel. Nice and straightforward in that front. And the other way then after that is our half-life, and that's the one that we need to look at in more detail, I suppose. Time taken, as I said, I got a quick definition for it there. The time taken for half of nuclei in a sample to decay. So we can calculate it mathematically using this. Log of 2 over our decay constant. Again, that's either going to be given to you or you can calculate it. And the same, you've got 3 parts, and we have one of them is always going to be a constant. That log of 2, we can pop it into our calculator and it's 0.6 something, 0.693, and that's never going to change. Same as we had for our speed of light value, say for example, it never changes. So the only 2 things that can alter are our decay constant and our half-life, depending on the sample and how much of a sample that we've got. So the calculations involved in these are really straightforward, to be perfectly honest. We're talking about half-life. It's how much of something goes away, or the time taken for half of it to decay or to disintegrate or to vanish, disappear. You can imagine if I've got a barrel of something, some radioactive material, and it's full to the brim, and it has a half-life of 10 years. You can imagine after 10 years it is going to be half full, because half of it has decayed. Another 10 years go by, it's going to be a quarter full, because it's halved again, and it will continue to half and continue to half. Now I know I mentioned this previously, the only and the big downside to this when we're talking about radioactive material, that it will never completely go away. If I keep halving something, it will always there will always be some remnants of it left, regardless of how long we're talking about. Now 10 years, as I said, it could be 100 years, or it could be 1,000 years of a half-life of some radioactive materials. So they will outlast a lot of other things. It will outlast me anyway, for sure. So the check that I wanted to show you, I've imagined, just to give you an idea, if I've got 1 kilo of a radioactive material, which is going to be there, and you can see I've got that down, and then I've got half-life of 1 hour. So I'm saying that the T of a half, or the half-life, is 1 hour in this case. And again, it was just to give us a quick example to how to see this. At the start of our measurements, I've got 1 kilo of my radioactive, and I've got a T of 0. So no time has gone. Brand new sample. After 1 hour, I'm going to have a half kilo. After 2 hours, I'm going to have a quarter kilo. And then I'm going to have 0.125, and then that's going to half again after 4 hours. And you can imagine we end up with essentially an exponential function. So you can see what's going on there. I'll do my best to draw as good a line as I can. But you can imagine that we're going to drop. Now, we want to look at this part specifically. You can see what's going on. I'm getting closer and closer to that x-axis for hours. The red line will never touch that x-axis. I'll never get to 0, because I will never be rid of this radioactive material. It drops massively in the first half-life, the second half-life, the third half-life, we can see how much it drops by. The amount that we lose each time gets a little bit smaller. But that red line is never going to hit there. You guys have probably looked at exponential functions in maths already. That red line is never going to cross the x-axis. I'm never going to have an x value of 0. There's always going to be some of that radioactive material left over, just to keep it in mind. But as I said, all of the maths involved in here, we can use the formula that was given to us. I'll just scratch that out and you can see it there again. T half-life, T half is equal to the log 2 over lambda, which is our decay constant. Alternatively, when we're doing these, there's a lot of calculations involving either multiplying by 2 or dividing by 2, because I'm either halving something or I'm figuring out how many halves or how many half-lives have we gone through. So it is straightforward enough. You just got to take our time, think about it logically, and we'll have no issue answering these problems. Fingers crossed that has made things a bit clearer for you. If you need any help, you know where to get me. Thank you very much.